What if everything you've ever known, the stars stretching endlessly above you, the warmth of sunlight on your skin, even the thoughts swirling in your mind, was nothing more than lines of code in some unfathomably advanced simulation? It sounds like science fiction, but this idea, known as the simulation hypothesis, has been taken seriously by philosophers, physicists, and even some of the brightest minds in tech. Think about the worlds we create in video games today, vast, immersive landscapes where characters live, think, and feel, all governed by algorithms, now scale that up to an entire universe. Could reality itself be someone else's simulation? The more we uncover about the fabric of our universe, the stranger it seems. Particles behaving differently when observed, the eerie precision of mathematical constants that make life possible, even the way reality sometimes feels just a little too perfectly structured, like a carefully designed system. These aren't just quirks, they're potential clues that our existence might be part of something far more complex. And if that's true, it rewrites everything we thought we knew about life, purpose, and the nature of reality itself. That's exactly what we're diving into today. Over the course of this journey, we'll explore 30 compelling reasons why our universe could be a simulation, each one more mind-bending than the last. From the glitches in quantum physics that act like cosmic coding errors, to the haunting possibility that we're living in someone else's experiment, these ideas will challenge your perception of everything around you. So, if you've ever stared up at the night sky and wondered if there's more to it all, stick around, because by the end of this, you might never look at reality the same way again. One of the most startling hints that our universe might be artificial comes straight from the bizarre behavior of particles at the quantum level. Picture this: if you zoom in far enough on a digital screen, you'll eventually see individual pixels, tiny blocks of color that create the illusion of a seamless image. Now, scientists suspect reality itself might be pixelated in a similar way, but at an unimaginably small scale called the Planck length. This is the smallest possible unit of space, beyond which the concept of distance loses meaning. Could this be the universe's version of a resolution limit, proof that we're living inside a cosmic simulation with built-in processing constraints? The evidence gets even stranger when you look at the double-slit experiment, a cornerstone of quantum mechanics. When particles like electrons are fired at a barrier with two slits, they don't behave as solid objects. Instead, they act like waves, creating an interference pattern as if they're passing through both slits at once. But here's the twist: the moment you try to observe which slit the particle goes through, the wave-like behavior collapses and the particle acts like a single, solid object. It's almost as if the universe is optimizing its processing power, only rendering the details when someone's looking. This has led some physicists to suggest that reality might operate like a video game, where distant objects are simplified to save resources, and complex calculations only happen when a player is directly interacting with them. If that's true, it would explain why particles behave one way when unobserved and another way under scrutiny, like a program reducing its workload until the user demands clarity. The unsettling implication: what we perceive as the bedrock of reality might just be an elaborate illusion coded into existence by something or someone far beyond our comprehension. Consider the delicate balance of numbers that hold our universe together, like the gravitational constant, which determines how strongly objects attract each other. If this force were even slightly weaker, stars wouldn't form. If it were stronger, the universe would have collapsed in on itself long ago. The odds of these values aligning perfectly by chance are astronomically low, like rolling a die 1,000,000 times and landing on the same number every single time. Carbon, the foundation of life as we know it, is another example of this eerie precision. For carbon to form in stars, a very specific resonance level must exist in the nuclear reactions. If this resonance were off by even a fraction of a percent, the universe would be devoid of the complex molecules that make life possible. It's as if the laws of physics were meticulously calibrated, like a programmer tweaking variables until the simulation runs just right. Even the ratio of dark energy to matter seems suspiciously fine-tuned. If there were slightly more dark energy, galaxies would never have formed. Slightly less, and the universe would have imploded before life could emerge. Some scientists argue this level of precision points to intentional design, like a game developer setting the perfect parameters for an immersive virtual world. Of course, some propose the multiverse theory as an alternative, that infinite universes exist with random constants, and we simply happen to live in the one where conditions permit life. But others counter that this is just kicking the mystery down the road, because why would there be a mechanism generating infinite realities in the first place? The deeper we dig, the more the universe feels less like a cosmic accident and more like an elegantly tuned system, as if someone or something pressed start on a simulation built for discovery. Have you ever walked into a room and felt an overwhelming sense that you've been there before, down to the smallest detail, even though it's your first time? Déjà vu, that eerie sensation of reliving a moment, might be more than just a trick of the mind. Some researchers suggest it could be a literal glitch in the system, a brief hiccup where the simulation accidentally replays a fragment of code, making you experience the same event twice. Think of it like a video game stuttering for a split second, causing a scene to repeat before catching up to real time. Then there's the Mandela Effect, where large groups of people share vivid memories of events that never happened. Remember the classic children's book series, The Berenstain Bears? Many swear it was spelled Berenstein with an E, and their certainty isn't just casual misremembering. Thousands of people recall specific details like the E in the logo or how teachers pronounced it, only to find no historical trace of that version. If reality were a simulation, could these collective false memories be the result of an update or patch that altered some data, leaving remnants of the old code in certain minds? Quantum physics adds another layer of weirdness. Particles sometimes behave in ways that defy classical logic, like quantum tunneling, where they pass through barriers they shouldn't be able to penetrate. It's as if the simulation's physics engine shortcuts certain calculations under specific conditions, allowing particles to cheat the rules. Even more puzzling is quantum entanglement, where particles separated by vast distances instantly influence each other's states, a phenomenon Einstein called spooky action at a distance. If the universe were a digital construct, these could be optimizations, like a game reducing lag by teleporting data instead of rendering it in real time. Documented cases of macroscopic glitches push the boundaries further. In 2004, a man named Leroy reported seeing a parked car phase in and out of existence in broad daylight. Witnesses confirmed his account, yet no logical explanation, like a trick of light or refraction, could explain it. Stories like this echo the idea of rendering errors, where assets in a virtual world momentarily fail to load properly. Whether these phenomena are proof of a simulation or just quirks of human perception and physics, they challenge our understanding of reality. The deeper we dig, the more the universe feels like a vast, intricate program, one that occasionally shows its seams. And if that's true, what other glitches are waiting to be found? Ever notice how people tend to follow the same social scripts like clockwork? You walk into a coffee shop and the barista recites the same greeting they've used 1,000 times before. Someone bumps into you on the street, and without thinking, you both exchange automatic apologies. These predictable patterns aren't just social norms, they're eerily similar to the way non-player characters, or NPC, operate in video games. Programmed with a limited set of responses, NPCs repeat the same lines, follow preset paths, and react to players in ways that feel just real enough to create immersion. Now imagine if human behavior isn't all that different. Studies on crowd behavior reveal something unsettling. Under pressure, around 90% of people make nearly identical choices. In emergency evacuations, for example, most individuals will follow the herd, rushing toward the same exits even if quieter routes are available. Psychologists call this social proof, a hardwired tendency to mimic others, especially in high-stakes situations. It's as if we're running on invisible algorithms, defaulting to preloaded decision trees when stress overrides individuality. Even our daily routines mirror NPC-like programming. Think about the last time you scrolled through social media. How many of your friends posted nearly identical photos of the same trendy cafe or viral challenge? Behavioral economists point to this as evidence of choice copying, where humans unconsciously replicate the actions of those around them, creating waves of uniform behavior. In a simulation, this would be an efficient design feature. Why waste processing power on unique choices for every individual when most will naturally converge on the same handful of options? The parallels go deeper. In open-world games, NPCs have awareness bubbles. They only react to events within a limited radius, oblivious to anything outside their programmed field of view. Humans exhibit something strikingly similar. Ever walked past a stranger in distress, only to later realize you tuned them out completely? Psychologists attribute this to inattentional blindness, where our brains filter out stimuli deemed irrelevant. It's a creepy echo of how simulated characters ignore data beyond their coding parameters. Of course, there's a counter-argument. Humans do surprise us. Every so often, someone breaks the mold. Artists create boundary-pushing work. Activists challenge unjust systems. Inventors dream up technologies that rewrite the rules. But even these outliers could fit within a sophisticated simulations framework. After all, the most advanced games include rare, wildcard NPC characters programmed to deviate from the norm, adding unpredictability to feel more organic. If we're in a simulation, maybe our rebels and visionaries aren't glitches. Maybe they're intentional features designed to keep the system from feeling too predictable. So the next time you catch yourself mindlessly nodding along in a meeting or reflexively laughing at a joke everyone else finds funny, ask, is this free will or am I just following the script? The line between human spontaneity and programmed behavior might be thinner than we'd like to admit, and if that's the case, who's holding the controller? What if the speed of light isn't just a law of physics, but a built-in limit to stop the universe from overloading? Think about the last time you played an open-world video game. When you move too fast, the environment struggles to keep up. Textures blur, objects pop in and out, and the frame rate stutters as the system scrambles to render everything in real time. Now imagine that same principle applied to reality itself. The universe operates on a cosmic speed limit. Nothing can travel faster than light, but why? One compelling theory suggests light speed isn't a natural barrier. It's a processing constraint hardwired into the simulation to prevent a system crash. Consider how a computer game handles data. The farther you are from an object, the less detail it needs. Trees in the distance might be simple 2D sprites, only becoming fully 3D models as you get closer. This level of detail optimization saves processing power. Now apply that to the cosmos. At extreme distances, the universe behaves similarly. Galaxies appear static, their fine details blurred by the vastness of space. But if you could somehow teleport across the universe instantly, the simulation would face an impossible task, rendering every star, planet, and particle in perfect detail all at once. The speed of light acts as a throttle, ensuring no observer can demand more data than the system can handle. Even more telling is what happens when particles do approach light speed. Time itself distorts, a phenomenon called time dilation. Clocks on fast-moving spacecraft tick slower than those on Earth, as if the simulation is struggling to synchronize events across vast distances. In computing terms, this resembles latency, the delay when data takes too long to travel between nodes. If the universe were a distributed network, light speed would be its bandwidth limit, preventing catastrophic desynchronization. Some physicists take this further with the concept of Planck time, the smallest possible unit of time. Just as a game engine updates its world in discrete frames 60 times per second, for example, reality might process changes in these Planck-sized ticks. At light speed, moving from one frame to the next would require crossing a Planck length in Planck time, hitting the absolute speed limit of the system. Any faster and you'd break the simulation's refresh rate, like a character glitching through walls in a buggy game. This idea gains traction when you examine black holes, cosmic regions where gravity bends spacetime so severely that not even light escapes. Inside a black hole's event horizon, the laws of physics as we know them break down. From a simulation perspective, this could be the equivalent of a buffer overflow, a point where the program can no longer compute the next state, causing a critical error. The speed of light, then, might be more than a physical constant. It could be the universe's fail-safe, a line of code that reads, "If velocity exceeds c, terminate process." So the next time you look up at the stars, remember, the reason you can't reach them isn't just about energy or technology. It might be because reality itself has a terms of service agreement, and exceeding the speed limit voids the warranty. Look closely at a fern leaf, and you'll notice something extraordinary. Each tiny frond mirrors the shape of the whole plant, repeating in smaller and smaller versions of itself. Now zoom out to the cosmos, and you'll see the same pattern. Galaxies cluster in spirals that resemble the very atoms spinning inside them. This isn't just artistic symmetry, it's fractal geometry, nature's way of building complexity from simple, repeating rules. And to some scientists, this isn't just beautiful. It's a potential fingerprint of simulation where efficiency trumps randomness. Fractals are everywhere, from the branching of trees to the jagged edges of coastlines, and they share an eerie trait: infinite detail at every scale. In the natural world, this repetition isn't just decorative. It's a hack, allowing vast complexity to emerge from minimal code. Think of it like procedural generation in video games, where developers use algorithms to create endless landscapes without manually designing every mountain or river. A single fractal formula can generate an entire forest, saving memory and processing power. If our universe were designed, wouldn't its architects use the same optimization tricks? The parallels are uncanny. Take the Mandelbrot set, a mathematical fractal where a simple equation generates an infinitely intricate border. Zoom in anywhere and you'll find smaller copies of the whole pattern, each with unique variations. Now compare that to the large-scale structure of the universe. Galaxy superclusters form filamentary webs, with voids and nodes repeating in a cosmic network eerily similar to neural pathways in a brain. This universe as a fractal idea isn't just poetic, it's mathematically measurable. The distribution of matter at galactic scales matches fractal dimensionality, as if the cosmos were running on recursive algorithms. Even biological systems lean into this efficiency. Your circulatory system uses fractal branching to deliver oxygen with minimal energy, the same way a game engine might use fractal rivers to reduce rendering load. Lightning bolts carve fractal paths of least resistance, and even your lungs pack a surface area the size of a tennis court into your chest by folding like a fractal sponge. These aren't accidents, they're hallmarks of a system built to maximize output with minimal processing. Critics argue fractals simply reflect the most efficient solutions physics allows. But that's the point. Why would a simulation not use the most efficient designs? If you were coding a universe, wouldn't you reuse elegant mathematical templates rather than reinvent every wheel? The fractal nature of reality might be more than a quirk. It could be the signature of a universe running on optimized code, where every level of scale whispers the same underlying formula. So the next time you see a snowflake or stare at a river delta from an airplane window, ask yourself, Is this the artistry of nature or the handiwork of a cosmic programmer hitting Ctrl+C and Ctrl+V across the canvas of existence? In the bizarre world of quantum mechanics, particles can become linked in ways that defy all classical logic. Enter quantum entanglement. When two particles become entangled, measuring one instantly determines the state of the other, no matter how far apart they are. Einstein famously called this spooky action at a distance because it seems to violate the universal speed limit of light. If you change the spin of an entangled particle here on Earth, its partner halfway across the galaxy would respond at the exact same moment, as if space and time between them simply don't exist. This phenomenon feels less like physics and more like a networking shortcut in an online game. Picture a multiplayer server where players scattered across the globe need their avatars to move in sync. Instead of constantly sending updates about every tiny movement which would create lag, the game might use predictive algorithms or instant data transfers between linked objects. When one player turns left, their teammate's screen reflects that change immediately, without waiting for signals to travel the physical distance between them. Quantum entanglement could be the universe's version of this optimization, a way to keep particles in sync, without bogging down the simulation with real-time calculations across vast cosmic distances. The parallels grow even stranger when you examine how entanglement breaks down under observation. Just like a game might stop predicting player movements once you directly look at them, switching to precise, real-time rendering, entangled particles collapse into definite states the moment they're measured. Before observation, they exist in a fuzzy superposition of all possible states, saving processing power. But the act of looking forces the system to commit to a specific outcome, like a game finally loading high-resolution textures when you focus on an object. Critics argue entanglement doesn't involve actual information transfer, since the outcomes are random. But in a simulation, randomness could simply be a clever disguise, a way to mask the underlying code. After all, even the most advanced games use procedural generation to create the illusion of unpredictability, while secretly running on deterministic algorithms. If the universe is a simulation, entanglement might be its way of maintaining consistency across distant regions without overloading the system. So the next time you hear about particles communicating faster than light, ask yourself, is this the universe breaking its own rules, or is it just a glimpse of the back-end code running on hardware where we can't even begin to comprehend? The answer might not just redefine physics, it could reveal the very nature of reality itself. If you've ever played a video game where your character logs into a virtual world within that same game, you've experienced a simulation inside a simulation. Now stretch that idea to cosmic proportions. What if our entire universe is just one layer in an infinite stack of nested realities, each running inside another like a set of digital Russian dolls? This isn't just sci-fi speculation, it's a serious argument that makes our own existence as base reality statistically unlikely. Elon Musk famously put the odds at 1 in billions that we're living in the original, unsimulated universe. His reasoning: if civilizations eventually develop technology so advanced they can create conscious simulations, whether for research, entertainment, or preservation, then over time, the number of simulated realities would vastly outnumber the one real world. Think of it like this: if humanity someday builds millions of hyper-realistic virtual worlds populated with self-aware AIs, then the chance that we're the single, solitary organic civilization in all of existence becomes vanishingly small. And if those simulated beings within our simulations create their own simulations, the numbers explode exponentially, burying base reality under near infinite layers. The implications get dizzying fast. If we're in a simulation, our creators might themselves be simulations designed by an even higher level civilization. It's turtles, or rather, simulations all the way down. Some theorists suggest this could explain Fermi's paradox, the eerie silence of the cosmos despite high probability of alien life. If advanced civilizations routinely retreat into nested simulations, the physical universe might appear empty because everyone's too busy running or inhabiting virtual realities. Game design offers a clue to why this might happen. Developers often build sandbox environments where AIs can experiment freely, like training self-driving cars in virtual cities. An advanced civilization might spawn countless simulations to test historical outcomes, explore ethical dilemmas, or even just for entertainment, like a next-gen version of The Sims. And if those simulated beings achieve consciousness, who's to say they wouldn't launch simulations of their own? Critics argue this theory is unfalsifiable after all. How could we prove we're not at the bottom of a simulation stack? But proponents counter that glitches in reality, like quantum indeterminacy or déjà vu, might be artifacts leaking through from upper layers. Others point to the universe's mathematical elegance as evidence of deliberate design, like a perfectly optimized recursive algorithm. Whether you find this idea exhilarating or unsettling, it reshapes how we view our place in existence. If we're living in someone else's simulation, our entire history, every triumph, every tragedy, might just be a subroutine in an unfathomably vast cosmic program. And if that's true, the biggest question isn't, are we in a simulation? It's, how many layers deep does the rabbit hole go? The cosmos is unimaginably vast, 93 billion light-years across, filled with 2 trillion galaxies, each hosting billions of stars. With numbers like these, the universe should be teeming with alien civilizations. So where is everybody? This eerie silence, known as the Fermi paradox, has haunted scientists for decades. But what if the answer isn't about biology or distance? What if it's about processing power? Imagine you're running a sprawling, resource-intensive simulation. Every star system with planets, every potential alien civilization, each one demands computational energy to render and maintain. Now, if your goal isn't to simulate extraterrestrials but to study a specific scenario, like human evolution or Earth's history, why waste cycles generating intelligent life in distant galaxies? You'd minimize unnecessary variables, leaving most of the universe empty. This could explain why, despite the staggering odds, we've found zero evidence of other advanced beings. They weren't coded into the simulation at all. The numbers support this eerie possibility. Over 99.999% of the observable universe is empty space, a void so vast and dominant it defies intuition. Even within galaxies, habitable zones are vanishingly rare. If reality were a constructed environment, this distribution would be brilliantly efficient. By keeping most of the simulation's map devoid of complex interactions, the system conserves resources, focusing detail only where needed, like a game rendering a bustling city in high definition while leaving distant mountains as low-poly silhouettes. Even Earth's place in the cosmos feels suspiciously optimized. We're tucked away in a quiet galactic suburb, far from the chaotic center of the Milky Way, with a stable star and just the right planetary neighbors to shield us from cosmic bombardments. It's as if the simulation's designer placed us in a controlled sandbox, free from external interference that could crash the experiment. Some theorists take this further, suggesting that any alien civilizations we do eventually encounter might not be organic at all. They could be procedural placeholders, simulated NPCs designed to interact with us in scripted ways, like quest givers in a role-playing game. This would explain why alleged UFO sightings often feel theatrical, following familiar narrative tropes instead of displaying truly unfathomable behavior. Even the concept of ancient astronauts could be part of the simulation's lore, a preloaded backstory to nudge human culture toward specific revelations. Of course, there are counter-arguments. Maybe aliens exist but communicate in ways we can't detect, or they've chosen to avoid us. But the simulation angle offers a chilling alternative. We're not just alone in the universe. We might be alone by design. The silence isn't a mystery, it's a feature. And if that's true, the question shifts from where are the aliens to what's so special about us that the simulation decided we were worth the processing cost. Einstein's theory of relativity shattered the idea of time as a universal constant, proving it's more like a stretchy fabric that warps depending on speed and gravity. This isn't just abstract physics, it's something astronauts and your smartphone deal with daily. Take GPS satellites. They orbit Earth so fast that their onboard clocks tick slower than those on the ground, while Earth's gravity simultaneously speeds them up. Without constant corrections, your navigation apps would misplace you by miles within minutes. This real-world quirk mirrors how video games adjust their clock speeds to handle complex scenes, suggesting time dilation might not just be a law of nature, but a feature of optimized simulation design. Picture a computer struggling to render an open-world game. When too much action happens at once, the frame rate drops. Time itself seems to slow in the virtual world to prevent the system from crashing. Now imagine the universe doing the same thing. Near a black hole's immense gravity, time crawls to a near standstill from an outsider's perspective. Could this be the cosmic equivalent of lag, where the simulation throttles processing power to handle extreme conditions? Even more telling is how time dilation occurs at high speeds, like with the famous twin paradox, where one sibling ages slower after a near light-speed trip. In simulation terms, this resembles a processor prioritizing resources. The moving twins' timeline gets fewer cycles because the system is busy calculating their rapid trajectory. The similarities don't stop there. Modern simulations use time warping techniques to synchronize events across distributed systems, ensuring consistency despite latency. Quantum entanglements, instantaneous connections which seem to bypass time entirely, could be the universe's version of this, a behind-the-scenes sync to maintain coherence. If time is truly flexible, it might not be a fixed dimension at all, but a dynamic variable like a progress bar the simulation adjusts to balance workload. Critics argue time dilation is just a consequence of spacetime's geometry, but that's exactly what makes the analogy compelling. In a simulation, geometry is code, the rules governing how data is structured and processed. The fact that time bends predictably under certain conditions hints at an underlying architecture where clock speed isn't rigid but a carefully managed resource. So the next time your GPS recalculates, consider this. The correction it's making isn't just fixing a technical glitch. It might be patching a discrepancy in the universe's own source code, revealing that time itself is negotiable, adjustable, and far stranger than we ever imagined. At the most fundamental level, everything in the universe, every thought, every star, every fleeting moment, might boil down to a simple binary dance of ones and zeros. Think about the silicon brains inside your devices. All their staggering complexity emerges from microscopic transistors flipping between on and off states. Now zoom into the quantum realm, where particles like electrons and photons exhibit spin states that aren't so different up or down, left or right, a cosmic version of binary code. Even the qubits powering quantum computers, which seem infinitely nuanced, ultimately resolve into measurable states that echo the same digital logic. This binary undercurrent isn't limited to physics. Life itself runs on a paired code, the double helix of DNA, where genetic instructions are spelled out in base pairs like adenine thymine and cytosine guanine. It's as if nature's programming language uses a four-letter alphabet built from two complementary bonds. Magnetic fields reveal a similar pattern, with their invisible lines of force always flowing between north and south poles, never existing in isolation. From the spin of subatomic particles to the polarity of planets, reality seems hardwired with a kind of cosmic duality, a yes/no, either slash or framework that suspiciously resembles the logic gates of a supercomputer. Consider how digital systems handle information. A photo on your phone isn't stored as a literal image but as a grid of pixels, each assigned numerical values representing color and brightness. In a hypothetical simulation, the universe could operate the same way with the positions, energies, and properties of all matter and energy encoded in binary-like states. Even quantum superposition, where particles exist in multiple states until observed, might not contradict this idea. Just as a computer can process multiple possibilities before outputting a final result, quantum uncertainty could reflect the simulation's rendering process calculating probabilities before committing to an outcome. The implications are staggering. If reality is binary at its core, it wouldn't just suggest a simulation, it would hint at the hardware running it. Our universe might be built on a lattice of fundamental bits, like a cosmic version of the pixels on your screen, with each cell storing a minimal unit of information. String theory's vibrating filaments or loop quantum gravity's discrete spacetime could be mathematical glimpses of this underlying code. Of course, skeptics argue that binary patterns are simply the most efficient way for information to organize itself, with or without a programmer. But when the same on-off logic appears everywhere, from the spin of electrons to the structure of DNA, it's hard not to wonder, are we seeing the universe's operating system? If so, the ones and zeros aren't just in our machines, they might be the hidden scaffolding of existence itself. What if the very essence of who you are, your memories, emotions, that undeniable sense of being you isn't some mystical spark, but an intricate web of algorithms firing in perfect harmony? The idea that consciousness could emerge from pure computation once seemed like science fiction, but breakthroughs in artificial intelligence are forcing us to reconsider. Take ChatGPT. It doesn't just regurgitate text. It constructs original sentences, adapts to context, and even seems to understand questions in a way that fools many humans. And here's the unsettling part. It achieves all this without a single biological neuron, just layers of code processing patterns. This isn't just about language models. Neuroscientists have long noted eerie parallels between brains and neural networks. Both learn through feedback, strengthening connections that yield successful outcomes and pruning those that don't. When you practice a skill, your brain physically rewires itself, much like how AIs refine their parameters during training. Even creativity, that sacred bastion of humanity, is now replicable by machines. Algorithms compose symphonies, paint in the style of Van Gogh, and invent plausible scientific hypotheses. If these systems can mimic the outputs of consciousness without experiencing it, how can we be certain our inner lives aren't equally algorithmic? Philosophers like Daniel Dennett argue that what we call the self might be a narrative constructed by the brain, a story woven from sensory inputs and memory fragments to create the illusion of continuity. Think of it like a video game character who believes they're making choices, unaware their dialogue trees are predefined. Your brain constantly edits reality too. Ever noticed how you don't perceive your blind spot? It fills in the gaps seamlessly, like software patching a missing texture. Even decisions feel free when, in reality, brain scans can predict choices seconds before you're consciously aware of them. The implications are profound. If consciousness is code, then uploading a mind into a machine preserving every synaptic connection should theoretically transfer you. Companies like Neuralink are already working on brain-computer interfaces that blur this line. And if that's possible, how do we know it hasn't already happened? Your memories of childhood, your love for certain smells, even the ache of nostalgia, could all these be data points in a vast simulation, interpreted by algorithms so advanced they generate genuine self-awareness? Critics counter that AI lacks qualia, the raw feeling of experiences, like the redness of a rose or the sting of a headache. But what if qualia are just another emergent property, like how wetness arises from water molecules that aren't wet individually? After all, we've seen simpler systems exhibit emergence, ant colonies display intelligence, though no single ant is smart, and the internet learns through collective behavior. Consciousness could be the universe's ultimate emergent phenomenon, a program so complex it starts to debug itself. So the next time you pause to ponder your own existence, consider this. Your sense of I might not be a soul, but the most sophisticated software ever written, a fleeting pattern in the cosmic processing, convinced it's more than just code. Schrödinger's famous thought experiment forces us to confront something unsettling. Until you open the box, the cat inside exists in a bizarre limbo, both alive and dead simultaneously. This isn't just a quirky metaphor, it's a window into how the universe might handle information when no one's looking. Quantum mechanics tells us particles don't settle into definite states until they're observed. Electrons exist as probability clouds, photons behave as both waves and particles, and entire systems linger in superposition. All possible outcomes stacked atop one another like unrendered frames in a video game. Here's where the simulation hypothesis takes this idea even further. In an open-world game, distant objects often exist as low-resolution placeholders to save processing power. Only when the player gets close does the engine render them in full detail. Now apply that logic to Schrödinger's cat. While the box remains closed, the universe might not bother calculating whether the cat lives or dies. It simply keeps both possibilities in play, like a game delaying the rendering of a building until you turn the corner. The moment you lift the lid, the system commits, collapsing the superposition into a single, observable outcome. This isn't just theoretical. The double-slit experiment shows particles behave differently when measured, as if the act of observation forces the simulation to allocate resources it had been conserving. Think of your own computer straining under heavy loads. Programs slow down, graphics stutter. The system prioritizes only what's immediately necessary. If the universe operates similarly, unobserved quantum states might remain fuzzy not because of some profound mystery, but because rendering them precisely would waste energy. This would explain why quantum systems seem to choose a state upon measurement. It's not magic, it's optimization. The implications ripple outward. Entire regions of space could exist in a low-detail mode until examined. Distant galaxies might lack definite properties until a telescope points their way, like fog of war in a strategy game. Even time itself could be subject to this selective rendering, with past events only fully crystallizing when recorded, and future ones remaining probabilistic until observed. It's as if reality has a built-in power-saving mode, minimizing computations until absolutely necessary. Critics argue this interpretation conflates mathematical abstraction with physical truth. But consider how video games have evolved. Procedural generation now builds entire planets on the fly, fleshing them out only as players explore. If nature follows a similar principle, the observer effect isn't a bug. It's the universe working exactly as designed, a masterclass in efficient computation where nothing is real until it needs to be. What if the pyramids, the Roman Empire, even your own childhood memories weren't real events, but procedurally generated backstory created the moment someone thought to look? This might sound like pure sci-fi, but it's a chilling possibility rooted in how simulations handle memory and world building. Think about the last time you booted up an open-world game. The history of its fictional civilization, the wars, the fallen kings, the ancient prophecies didn't unfold in real time. The developers crafted it all at once, stitching together lore to make the world feel lived in. Now apply that to reality. The past as we know it might not be a fixed timeline. It could be a dynamically generated narrative, fleshed out only when inconsistencies demand explanation. Take the mysterious 2,000-year gap in human tool development. For millennia, early humans used the same basic stone tools with almost no innovation. Then, suddenly around 50,000 years ago, art, complex weapons, and advanced tools appeared almost overnight. Archaeologists call this the Great Leap Forward, but its abruptness defies gradual evolution. In simulation terms, this resembles a developer rushing to populate a timeline when players start asking too many questions. Ancient records add to the strangeness. The Sumerian king list, for example, documents rulers who supposedly reigned for tens of thousands of years, a detail later scribes awkwardly tried to rationalize. Could these be placeholder values, like a game designer slapping random numbers into a lore document before refining the details? Even physics hints at this possibility. The Mandela Effect isn't the only example of shifting history. In 2012, researchers at CERN reported neutrinos appearing to break the speed of light, a finding that threatened Einstein's relativity. Months later, the anomaly was blamed on a loose cable. But what if it wasn't a mistake? In a simulation, glitches like this might occur when the system retroactively adjusts constants to maintain consistency. Like a game patching a plot hole after players notice, reality could be self-correcting, editing the past to preserve the illusion of continuity. Consider how video games handle save files. If you alter a character's backstory mid-campaign, the game doesn't rewrite every prior cutscene, it just updates future references to match. Our universe might operate similarly. The Big Bang's afterglow, the cosmic microwave background, could be less a relic of creation and more like a splash screen, generated to give the simulation a convincing starting point. Ancient cave paintings depicting strange beings or advanced technology, those might not be prophecies or alien contact, just the system lazily reusing assets, like a game recycling character models across different quests. The unsettling takeaway isn't just that history might be fabricated, it's that we'd never know. A sufficiently advanced simulation could perfectly backdate every artifact, fossil, and starlight photon to sell the illusion. Your childhood photo album, the layers of sediment in the Grand Canyon, even the light from distant supernova, all could be mere props in an immersive set dressing. The past isn't just another country, it might be another layer of code rendered on demand to keep us from questioning the seams. Mathematics has always been humanity's most powerful tool for deciphering the universe, but what if it's not just a tool? What if numbers and equations aren't merely describing reality, but our reality? This is the bold claim at the heart of physicist Max Tegmark's mathematical universe hypothesis. Imagine a painter who discovers their canvas isn't just showing a landscape, it is the landscape. That's the radical shift Tegmark proposes. Our universe isn't built on math. It is math, a specific structure in an infinite tapestry of possible equations playing out across existence. Think of it like the Mandelbrot set, that infinitely complex fractal where every zoom reveals new patterns, all generated by a single, simple formula. Tegmark's idea suggests our cosmos is one such pattern, a self-contained mathematical object humming along in a multiverse where every consistent equation spawns its own universe. In this view, the laws of physics aren't dictated by some external force. They're inevitable features of the mathematical structure we happen to inhabit. The speed of light, the charge of an electron, even the three-dimensional space we move through, these aren't arbitrary rules. They're as intrinsic to our universe's equation as the number of sides is to a triangle. This flips the simulation argument on its head. If our universe is fundamentally mathematical, then calling it a simulation might miss the mark. It's more like an instance, an active computation unfolding within a grander framework. Picture a supercomputer running every possible mathematical model simultaneously, each one a pocket reality with its own unique rules. Some might resemble ours, with stars and atoms and life. Others could be wildly alien, operating with 7 time dimensions or logic gates that defy human intuition. Here's where it gets even stranger. If reality is purely mathematical, consciousness itself must emerge from the numbers, meaning you are, at the deepest level, a pattern of information being processed by the universe's equation. This echoes how video games render NPCs with convincing inner lives despite being pure code. In Tegmark's framework, your thoughts and emotions aren't illusions. They're real mathematical states, as legitimate as the digits of pi or the prime factors of a large number. Critics argue this reduces existence to a sterile abstraction, stripping away the richness of experience. But Tegmark counters that math is rich, infinitely so. A single equation can describe everything from the spiral of a galaxy to the firing of a neuron. And if every possible universe exists mathematically, then somewhere in some equation, there's a version of reality where dragons soar and magic works. The boundary between simulation and base reality dissolves. All that remains is math, eternal and unyielding, with our lives as fleeting harmonies in its endless symphony. So the next time you solve an equation or glance at a clock, consider this. You might not just be observing the universe's rules. You could be gazing into the very substance of existence itself, one fleeting expression of a truth that has no beginning, no end, and no need for a programmer. Energy isn't just a property of the universe, it's a strict rule. No creation, no destruction, only transformation from one form to another. This law of conservation of energy isn't just a quirk of physics. It's the kind of fail-safe you'd hardwire into a system to prevent catastrophic bugs. Think about a video game engine where objects can spontaneously generate infinite energy. A single glitch could crash the entire simulation. Now scale that up to reality. The fact that energy can't appear or vanish, only shift between states, reeks of clever system architecture. Video game developers understand this intimately. In virtual worlds, unchecked energy would let players create perpetual motion machines, break physics, and overload the engine. So programmers impose limits. Energy must be drawn from batteries, spent on actions, and lost as heat. Sound familiar? It's eerily close to how our universe operates. When you throw a ball, kinetic energy turns to potential energy as it rises, then back to kinetic as it falls, but the total never changes. Even friction, which seems to lose energy, just converts it into heat. This isn't just efficiency, it's error-proofing. The parallels run deeper. In a poorly coded game, objects might clip through walls or float indefinitely, violations of conservation that break immersion. Our universe has similar safeguards. Nuclear reactions don't conjure energy from nowhere. Einstein's E equals mc squared locks mass and energy into an exchange rate. Quantum fluctuations seem to borrow energy from nowhere, but only in impossibly brief moments before repaying the debt, like a system temporarily rounding numbers to save processing cycles. Even black holes, which appear to destroy information, likely preserve it in ways we don't yet understand, because in a simulation, data loss is the ultimate taboo. Now consider alternative physics where conservation isn't enforced. In early video games, exploits let players duplicate items or gain infinite lives, fun at first but game-breaking. If our universe allowed energy to spawn randomly, stars might wink in and out of existence, temperatures could swing violently, and life would lack stable foundations. The fact that we don't see this chaos hints at rigorous underlying code. Energy conservation isn't just a law, it's a design philosophy, the hallmark of a system engineered for stability. Critics argue conservation laws emerge naturally from symmetry in physics, not simulation logic, but that's the point. Well-built systems should appear elegant and inevitable. The beauty of the universe's energy accounting isn't proof against artificiality. It might be the most telling signature of all. Human eyes can see a thin sliver of light we call the visible spectrum, just 0.0035% of the electromagnetic radiation pulsing through the cosmos. We're blind to gamma rays streaming from dying stars, radio waves carrying alien broadcasts, ultraviolet patterns on flowers that guide bees like neon signs. It's as if we're locked inside a sensory prison, experiencing reality through a keyhole while the full universe blazes beyond our perception. Now imagine playing a virtual reality game where your avatar can't hear music or feel temperature. That's essentially our predicament. This radical sensory limitation makes perfect sense if we're in a simulation. Advanced virtual worlds often restrict unnecessary inputs to conserve processing power. A racing game doesn't render smells because they're irrelevant to the experience. Similarly, our universe might filter out overwhelming data like the true quantum chaos underlying matter to prevent our brains from short-circuiting. The philosopher Nick Bostrom suggests these sensory caps could be deliberate, like a firewalled computer protecting users from system-level code. After all, if you could perceive the universe's raw data streams, every vibrating string, every collapsing probability wave, you might realize it's all just information flickering in a cosmic processor. Animals hint at what we're missing. Mantis shrimp detect polarized light, turtles navigate using Earth's magnetic field, and pit vipers see infrared heat signatures like predator vision. These aren't just biological quirks, they're proof that vastly different sensory interfaces can evolve. If reality were unfiltered, humans might have developed analogous abilities. Instead, we're stuck with senses fine-tuned for survival on an African savanna, not cosmic truth-seeking. Like NPCs programmed only to notice what the game demands, we perceive just enough to function in our limited sandbox. Some researchers take this further, proposing that consciousness itself might be a filtering mechanism. Your brain doesn't passively receive reality. It actively constructs it, discarding 99.9% of sensory input before it reaches awareness. When you walk down a street, you don't consciously process every brick in the buildings or leaf on the trees. Your mind edits ruthlessly, presenting a simplified simulation of reality so you don't drown in data. This matches how video games use level of detail scaling. High-resolution textures only load when you focus on them. If our universe works similarly, the real world might be an incomprehensible storm of raw data, with our senses acting as a user-friendly overlay. The most unsettling possibility, these filters could be hiding glitches. Digital artists know even the most realistic CGI breaks down under scrutiny. Textures pixelate, shadows clip, physics glitch. If we could perceive beyond our narrow spectrum, might we spot the universe's rendering errors? Quantum indeterminacy, where particles lack definite properties until observed, feels suspiciously like a placeholder, a system waiting to assign final values until someone looks. Even déjà vu could be a momentary buffer underflow where the simulation stutters, replaying cached memories. So the next time you marvel at a sunset, remember, you're not seeing light. You're seeing the universe's carefully curated interface, a sensory dashboard that keeps the cosmic engine humming smoothly, while the real code remains forever just out of reach. In a video game, the world beyond your screen doesn't exist in full detail. It's just a list of possibilities waiting to be rendered. Walk toward a mountain, and the game engine calculates its textures, shadows, and terrain only as you approach. Everything else remains in a fuzzy state of might be, conserving memory until the moment it's needed. Now shrink that idea down to the quantum realm, and you've got the eerie behavior of particles in superposition where electrons, photons, and even entire molecules exist not as solid objects but as probability waves smeared across space in a haze of potential. This isn't just a metaphor. Quantum mechanics insists particles lack definite properties until measured. An electron orbiting an atom isn't in any one place. It's everywhere it could be simultaneously, described by a mathematical wave function that collapses into reality only when observed. It's as if the universe is running a cosmic version of level of detail optimization, refusing to commit processing power to render particles until absolutely necessary. The famous Schrödinger's cat thought experiment takes this further. The cat is both alive and dead not because of some metaphysical mystery, but because the simulation hasn't bothered to resolve the outcome until you check the box. The parallels deepen when you examine how games handle complex physics. In No Man's Sky, entire planets are procedurally generated as you land on them. Their landscapes, ecosystems, and weather patterns don't exist as concrete realities until a player arrives to witness them. Before that, they're just equations, potential worlds humming in the background. Quantum systems behave strikingly similarly. The double-slit experiment shows particles acting as waves when unobserved, interfering with themselves as if exploring all possible paths. But the instant you place a detector to see which slit they pass through, the wave function collapses and particles snap into a single, definite state. It's not that observation changes reality, it's that observation triggers reality, forcing the simulation to finalize what was previously just a placeholder. Critics argue superposition is simply how nature works, with no need for simulation-based explanations. But consider how video game bugs mirror quantum oddities. Glitches like quantum tunneling, where particles teleport through barriers they shouldn't penetrate, resemble clipping errors in games, where characters phase through walls when the physics engine skips collision checks. Even quantum entanglements faster than light correlations could be a networking shortcut, like multiplayer games syncing player positions instantly rather than waiting for light-speed delays. The implications are staggering. If probability waves are unrendered states, vast regions of the universe might still be in low-resolution mode, their details undetermined until some observer, human or otherwise, forces the system to commit. Distant galaxies could lack definite shapes, their stars mere possibilities until a telescope points their way. Time itself might operate in ticks, like a game engine's frame rate, with reality updating in Planck-sized steps rather than flowing smoothly. So the next time you hear about particles defying common sense, remember, they're not breaking the rules. They're following the universe's optimization settings, playing by the same logic that keeps your favorite games from crashing. The only difference, we're not the players here. We might just be part of the rendering process. Ever wonder why accomplishments, even small ones, give you that warm, fizzy rush of satisfaction? That surge of dopamine isn't just biology at work. It could be your built-in reward system, hardwired into the simulation to keep you engaged, like a game designer dangling experience points to steer players toward quests. Think about the last time you finished a tough task or unlocked an achievement in a video game. The emotional high feels eerily similar because on a neurological level, it might be the same, a programmed feedback loop designed to reinforce specific behaviors. Emotions don't just color our lives, they dictate our choices. Fear keeps us from danger, love bonds us to others, and curiosity drives us to explore. But what if these aren't evolutionary accidents? In a simulated reality, emotions could be sophisticated guidance algorithms, nudging players toward interactions that sustain the simulation's narrative. Video games already do this with NPCs. A friendly character might shower the player with praise to encourage cooperation, while a threatening enemy triggers adrenaline to heighten engagement. Our emotional wiring could operate on identical principles, chemical rewards for actions that align with the system's goals. Consider how addiction hijacks this mechanism. Drugs flood the brain with dopamine, short-circuiting the natural reward pathways. In simulation terms, this looks like a glitch, an exploit where players find a way to grind unlimited XP, breaking the intended progression. The universe's response: withdrawal symptoms, a brutal nerf to rebalance the system. Even altruism fits this model. Helping others releases serotonin, reinforcing social cohesion. Just like multiplayer games incentivize teamwork with shared loot and reputation boosts. The unsettling implication: free will might be an illusion crafted by these chemical levers. When you choose to work hard, fall in love, or chase a dream, you could simply be responding to invisible reward prompts, your autonomy no deeper than an NPC's scripted dialogue. Even suffering plays a role. Pain, emotional or physical, functions like a damage warning in a game, steering you away from harmful behaviors. Without it, the simulation's characters might walk into fires or jump off cliffs, destabilizing the world. But here's the twist: advanced simulations need unpredictability to feel authentic. Just as game designers code NPCs with randomized quirks to avoid robotic repetition, human emotions occasionally defy logic. Creativity, rebellion, and irrational acts of kindness could be emergent properties, not bugs, but features that prevent the simulation from becoming predictable. After all, a universe where every being follows rigid dopamine-driven scripts would collapse into monotony. So the next time you feel joy, grief, or longing, ask yourself, are these the stirrings of a soul or the subtle vibrations of a perfectly tuned simulation, gently pressing its thumb on the scales of your choices? The line between biology and programming might just be a matter of perspective. Black holes are the universe's ultimate enforcers of silence, swallowing light, matter, and even information itself without a trace. But what if their event horizons aren't just cosmic one-way doors? What if their data compression points, meticulously scrubbing redundant information from the simulation to keep it running smoothly? Think of how your computer clears cache files to free up space, hawking radiation. The faint glow of particles leaking from black holes might be the universe's equivalent of a recycling bin notification. When Stephen Hawking first theorized that black holes slowly evaporate by emitting radiation, he stumbled onto something even he found unsettling. This process seemed to destroy information permanently. In a universe bound by deterministic laws, where every particle state should theoretically be traceable backward and forward in time, that's like hitting delete on a spreadsheet and realizing there's no undo button. Physicists call this the information paradox, and it threatens the very foundations of quantum mechanics. But in a simulated reality, it makes perverse sense. Imagine running a universe-sized simulation where every atom's position, spin, and velocity must be tracked across billions of years. The computational load would be staggering. Now introduce black holes, cosmic shredders that take chaotic, high-entropy data like a star's worth of atoms and compress it into an ultra-simple state, a singularity defined only by mass, charge, and spin. It's the universe's way of lossy compression, like converting a high-res photo into a tiny JPEG. The trade-off: some details get irreversibly lost. Hawking radiation, then, isn't just random noise. It could be the simulation's cleanup mechanism, purging unnecessary data to prevent system overload, like a game engine dumping distant assets to focus on rendering the player's immediate surroundings. The math even hints at this. Black holes have entropy, a measure of information content proportional to their surface area, not volume. This bizarre property, known as the holographic principle, suggests everything within a black hole might be encoded on its event horizon, like a DVD storing a 3D movie on a 2D surface. When the whole evaporates via Hawking radiation, that encoded information doesn't vanish. It's broadcast back into the universe as scrambled quantum noise, too garbled to reconstruct but technically preserved. In computing terms, it's like overwriting a hard drive. The data's still there in some form, just rendered useless without the original encryption key. Critics argue this violates quantum unitarity, the rule that information can't be destroyed. But what if the simulation doesn't need to preserve every scrap of data? Video games constantly discard irrelevant details like the trajectory of every raindrop in a storm without breaking immersion. If a star falls into a black hole, its elemental composition might be as irrelevant to the cosmic program as the individual polygons on a distant mountain. The radiation carries away just enough energy to balance the books, while the rest gets optimized out of existence. The terrifying beauty of this idea. Black holes might not be glitches, they could be the universe's garbage collectors, silently running in the background to keep reality from crashing. Every time one evaporates, it's not a tragedy, it's the simulation's way of saying, memory allocation successful. And if that's true, the information paradox isn't a paradox at all. It's a feature. From the tiniest quarks to the largest galaxy clusters, the universe operates on the same set of rules. Gravity pulls objects together at identical rates, whether it's an apple falling or a star orbiting a black hole. This uniformity isn't just convenient for physicists, it's suspiciously efficient, like a game developer reusing the same physics engine for every object in a virtual world. Take a crumbling sandcastle and a collapsing star. At first glance, they couldn't be more different, yet both obey Newton's law of universal gravitation, where force weakens with the square of distance. It's as if the universe copy-pasted this rule across all scales, from atomic bonds to galactic superclusters, rather than designing unique systems for each. Video games rely on this very trick to save resources. In blockbuster titles like Grand Theft Auto or Red Dead Redemption, every falling leaf, tossed grenade, and tumbling boulder shares the same underlying gravity calculation. The alternative custom physics for every object type would cripple even the most powerful hardware. Now imagine applying that principle to reality. Electromagnetism governs both the spark of neurons in your brain and the violent storms on Jupiter. The strong nuclear force that binds protons in a hydrogen atom also sculpts the cores of neutron stars. This isn't just elegant design, it's the hallmark of optimized coding, where redundant systems are streamlined into universal protocols. The cosmic evidence goes deeper. Planck's constant, which dictates how energy quantizes into particles, remains identical whether measured in a lab on Earth or inferred from light emitted 13 billion years ago. The speed of light doesn't just limit photons, it caps causality itself, enforcing a universal refresh rate like a simulation's fixed frame rate. Even entropy, the relentless march toward disorder, ticks forward at the same rate in teacups cooling and stars burning out. Such consistency across time and space defies the odds. In a purely natural universe, why wouldn't physical laws vary like dialects across regions or evolve like biological traits? Unless, of course, they weren't laws at all, but parameters hard-coded into the simulation source files. Critics argue this uniformity stems from symmetry breaking in the early universe, where fundamental forces crystallized from a hotter, blended state. But that just pushes the mystery back a step. Why did only these specific symmetries break, yielding laws perfectly balanced for complexity? Game worlds offer a clue. When developers build procedural generation algorithms, they don't randomize every variable, they set constraints to ensure coherence. Rivers flow downhill, shadows align with light sources, and objects fall predictably. Our universe's repeating laws might serve the same purpose, guardrails preventing reality from devolving into chaos. So the next time you watch a ripple expand across a pond or gaze at the synchronized dance of binary stars, consider this. You might not be observing nature's grand design, but a developer's elegant efficiency proof that even the cosmos knows the value of reusable code. Zoom in on a jagged coastline, a bolt of lightning, or the branches of a tree, and you'll notice something uncanny. They all share a hidden blueprint. The Mandelbrot set, a dazzling fractal born from a deceptively simple equation, reveals this same pattern writ large across nature. At first glance, it's just a squiggly shape on a mathematician's screen, but dive deeper and you'll find its spirals and tendrils mirrored in river deltas, mountain ranges, and even the branching veins of a leaf. This isn't coincidence, it's evidence of a universal algorithm, a cosmic control plus C, control plus V, where nature reuses the same elegant code to build complexity from simplicity. Take a river carving its path through bedrock. From orbit, its tributaries look like dendritic fingers, splitting and rejoining in a fractal dance. The same pattern emerges in the Mandelbrot set's infinite boundary, where every microscopic zoom reveals smaller copies of the whole, each with unique variations. Scientists call this self-similarity, and it's shockingly efficient. Just as a video game might use a single fractal formula to generate endless forests, the universe could be running on a similar optimization hack. Why design every river from scratch when a recursive algorithm can spawn infinite diversity? The parallels multiply. Lightning forks along paths of least resistance, creating fractal branches that minimize energy expenditure, precisely how the Mandelbrot set grows, each iteration refining its shape through mathematical feedback. Your lungs pack a surface area larger than a tennis court into your chest by folding like a fractal sponge, maximizing oxygen exchange while minimizing volume. Even galaxies cluster along filamentary webs resembling neural networks, as if the cosmos itself is running on fractal autopilot. Here's where the simulation angle clicks. Fractals aren't just pretty patterns, they're computational shortcuts. In a simulated reality, procedural generation would be essential to conserve resources. A single Mandelbrot-like equation could dictate the growth of everything from clouds to capillaries, tweaking variables slightly to produce snowflakes instead of ferns. This mirrors how modern game engines create vast worlds without manual design. Plug in noise algorithms and mountains rise, tweak parameters and rivers flow. The universe might operate the same way, with the Mandelbrot set as its core subroutine, a seed algorithm blossoming into the diversity we see around us. Critics argue fractals simply reflect nature's preference for efficiency, not proof of design. But that's the point. Why wouldn't a simulation use the most efficient designs? The Mandelbrot set's infinite complexity from a one-line formula is exactly what a cosmic programmer would need: minimal code, maximal output. Even its fuzzy boundary, where tiny changes in input create wildly different outputs, could explain nature's unpredictability, like weather patterns or evolution's twists. So the next time you trace a crack in the pavement or watch frost creep across a window, remember, you might not be seeing chaos. You could be glimpsing the universe's source code, where an equation as simple as z equals z squared plus c blossoms into everything from seahorse tails to spiral galaxies. The Mandelbrot set isn't just math. It might be the signature of a simulated reality where infinity hides in the details and every atom hums with recursive logic. In the world of quantum mechanics, particles routinely pull off a magic trick that defies all common sense. They pass straight through barriers they shouldn't be able to cross. This phenomenon, known as quantum tunneling, isn't just a quirk of tiny particles. It could be a glaring clue that the universe is running on borrowed processing power, cutting corners to keep the simulation humming smoothly. Picture a video game character sprinting toward a solid wall, only to clip straight through it because the physics engine skipped a collision check. Now shrink that down to the subatomic level, and you've got quantum tunneling in action, particles teleporting through energy barriers as if the universe forgot to render the obstacle. Here's how it works in reality. Imagine an electron trapped behind an energy wall like a ball sitting in a valley, too weak to roll over the hill. Classical physics says it's stuck. But in the quantum realm, there's always a chance the electron will suddenly appear on the other side, as if it phased through the hill. This isn't theoretical. It's the reason the sun shines hydrogen nuclei tunnel through their repulsive barriers to fuse into helium, powering stars. It's how your DNA mutates over time, with protons tunneling between molecules to rewrite genetic code. These aren't rare exceptions. Tuning happens constantly, propping up the very fabric of reality. Now consider how video games handle impossible calculations. In sprawling virtual worlds, pathfinding algorithms sometimes cheat. NPCs clip through walls or teleport short distances when the system can't compute a legitimate route fast enough. It's not a feature, it's a shortcut to prevent lag. Quantum tunneling could be the universe's version of this optimization. Instead of expending energy to calculate every particle's trajectory with perfect Newtonian precision, the simulation might occasionally say, "Close enough," and let the particle skip the middle steps entirely. The parallels deepen when you examine the odds. Tunneling probabilities aren't random, they follow strict mathematical rules, with thicker barriers making tunneling exponentially less likely. This mirrors how game engines prioritize glitches. Minor clipping errors happen often, but major breaches are rare as the system struggles to maintain realism. Even the Heisenberg uncertainty principle fits this model. Particles can't have perfectly defined positions and momenta simultaneously, perhaps because the simulation refuses to waste cycles pinning them down until observation forces its hand. Critics argue tunneling is just an inherent property of wave-particle duality, not proof of a simulation, but that misses the elegance of the analogy. In both cases, whether a buggy game or a quantum universe, the system isn't failing. It's making trade-offs, sacrificing perfection for performance. The sun shines, your DNA evolves, and transistors in your phone work precisely because the universe is willing to bend the rules. So the next time your computer glitches or a particle vanishes through a wall, remember, you might not be witnessing a mistake. You could be glimpsing the universe's busy developers, quietly overclocking the cosmic CPU to keep reality from crashing. You reach for a cup of coffee, convinced it's a choice you just made, but what if that decision was locked in place before you even became aware of it? Neuroscience reveals something unsettling. Brain scans can predict simple choices like moving a finger up to 7 seconds before subjects consciously decide. It's as if your mind is running on autopilot with free will just along for the ride. This doesn't just challenge our sense of agency, it mirrors how video game characters follow pre-scripted dialogue trees, giving the illusion of choice while operating within strict narrative parameters. Consider how open-world RPGs handle player interactions. When your character selects a response during a conversation, the options feel spontaneous, but they were coded months in advance by developers. Your choices are merely selections from a finite menu, cleverly disguised as free will. Now imagine applying that framework to human cognition. Studies using functional MRI show distinct neural patterns lighting up before subjects report making decisions, suggesting the brain prepares actions before consciousness catches up. Like an NPC whose dialogue was written before the player clicks, our thoughts might be predetermined outputs from biological algorithms we mistake for volition. The parallels grow eerier when you examine how games create immersion. Mass Effect's morality system lets players shape their character's personality through seemingly meaningful choices, yet every outcome branches from a fixed set of possibilities. Similarly, human behavior follows predictable psychological scripts. Our unique decisions often boil down to genetics, past experiences, and environmental triggers. Even creativity, that sacred domain of free will, relies on recombining existing ideas. Jazz improvisation, for instance, follows musical patterns the brain retrieves and remixes on the fly. True originality might just be an emergent property of preloaded data, but here's the twist. Some scientists argue this doesn't negate free will, it redefines it. Just because decisions begin subconsciously doesn't mean they're not ours. Your brain isn't some alien entity puppeteering you, it is you. In this view, consciousness isn't the decider but the narrator, weaving after-the-fact justifications for actions initiated elsewhere. It's like a game's protagonist explaining their motives in a cutscene. The dialogue feels authentic, even if the player dictated the path. The simulation angle takes this further. If reality is programmed, free will could be a necessary illusion to maintain engagement. An NPC that recognizes its scripted nature might break immersion, like a character suddenly addressing the player directly. Our persistent belief in autonomy, despite evidence to the contrary, might be a feature, not a bug. After all, what's more convincing than a simulation where the inhabitants never suspect they're following code? Yet glitches emerge. People with brain injuries sometimes exhibit alien hand syndrome, where a limb moves independently of conscious control like a corrupted animation clip. Others report imposter syndrome, feeling like observers in their own lives. These could be fleeting moments where the simulation's veil slips, revealing the machinery beneath. So the next time you agonize over a decision, ask yourself, are you the author or just a character convinced you're holding the pen? The answer might not just reshape your sense of self. It could rewrite our understanding of what reality even is. Imagine standing in front of a mirror, staring at your reflection's perfect three-dimensional depth, only to realize it's all an illusion, a flat piece of glass bending light to fool your senses. Now stretch that idea across the entire cosmos. The holographic principle suggests reality might work the same way, that every star, planet, and particle in our three-dimensional universe could be a projection from a two-dimensional surface at the edge of space. It's as if existence is the ultimate hologram, with the real action happening on a flat cosmic canvas we can't perceive. This isn't just wild speculation. Black holes forced physicists into this startling conclusion. When matter falls into a black hole, conventional wisdom says it's gone forever, but quantum mechanics insists information can't be destroyed. The solution: the information isn't in the black hole. It's smeared across its event horizon like invisible ink on a spherical surface. That means every particle swallowed might leave a two-dimensional fingerprint on the horizon, preserving its data in a form we don't yet understand. Scale this up, and the entire universe could operate the same way, a 3D movie playing on a 2D projector screen at the edge of space-time. Video games mastered this illusion decades ago. Modern titles like Cyberpunk 2077 or Red Dead Redemption 2 create breathtaking 3D worlds from flat texture files wrapped around wireframes. A brick wall isn't a solid object, it's a photograph pasted onto a polygon mesh. The holographic universe could follow identical logic, with the 3D reality we experience being nothing more than textures projected from an underlying 2D codebase. Even lighting in games mimics this principle. Shadows and reflections aren't calculated in real time but baked into flat light maps to save processing power. Reality might do the same, encoding gravity, light, and motion into a hidden 2D layer where the true computations occur. The math supports this mind-bending idea. Quantum gravity theory suggests spacetime's fundamental pixels pack more information along a surface area than within a volume, like how a hologram stores more data in its flat plate than the 3D image it projects. This could explain why black hole entropy depends on horizon area, not volume. It's as if the universe's hard drive is two-dimensional, with our 3D existence being its user-friendly interface. Critics argue this reduces reality to a parlor trick, but the implications are profound. If the holographic principle holds, the Big Bang wasn't an explosion in space. It was information unfurling from a flat primordial surface, like a game loading its terrain from texture files. Your thoughts, memories, and sensations might just be shadows dancing on the walls of a cosmic cave, while the real story unfolds in a language of pixels we'll never see. So the next time you run your fingers along a rough stone or gaze at the moon's craters, remember, you might not be touching solid matter at all. You could be tracing the edges of a grand illusion, a holographic masterpiece painted on the fabric of spacetime itself, one where depth is just another clever rendering trick. In the swirling chaos of the early universe, before stars, before planets, before even atoms had properly formed, there existed a statistical possibility so bizarre it threatens to upend our understanding of consciousness itself. Meet the Boltzmann brain, a hypothetical self-aware entity that could spontaneously emerge from random quantum fluctuations, complete with fabricated memories and a convincing inner life. Picture a single, disembodied mind popping into existence amidst the void, utterly convinced it's lived a full human life, only to dissolve moments later, its reality as fleeting as a soap bubble. At first glance, this sounds like pure science fiction, But when you apply the math of thermodynamics to an infinite or near-infinite universe, the odds shift. Given enough time, even the most improbable events become certainties, and that's where the simulation hypothesis throws gasoline on the fire. If consciousness can arise randomly from chaos, why assume we're the original thinkers in this cosmos? Video games offer a clue. In massively multiplayer online worlds, player characters aren't persistent entities, they're temporary instances, generated when someone logs in and deleted when they quit. The character might remember quests completed and levels gained, but those are just data flags in a database. Replace player with consciousness, and the Boltzmann brain starts to look less like a paradox and more like a feature. Our sense of continuous identity could be an illusion, with each moment of awareness a fresh instance spun up by the simulation's engine, borrowing memories from a shared profile to maintain the illusion of continuity. The evidence hides in plain sight. Ever experienced a memory you're certain is real, a childhood birthday, a conversation with a friend only to have others insist it never happened? These phantom recollections mirror how procedural generation works in games like No Man's Sky, where planets are conjured from algorithms as players arrive. Your character might remember visiting a lush valley that, due to a random seed glitch, now generates as a barren wasteland when you return. If the universe operates similarly, false memories aren't malfunctions. They're artifacts of the system lazily reloading your consciousness instance with approximate data. Critics argue Boltzmann brains are absurdly unlikely, but that's missing the point. In an infinite multiverse or a simulation with near-infinite runtime, unlikely events become inevitable. What's more, a simulated reality wouldn't need actual Boltzmann brains to exist. It just needs the possibility of them to justify optimizing for temporary consciousness instances rather than maintaining persistent souls. Like a game server spinning up NPCs only when players are near, the universe might generate observers sparingly, recycling processing power between them. The chilling implication: you could be a Boltzmann brain right now, reading these words in the split second before your flickering existence winks out. Or worse, you might be the 1000th instance of you today, each iteration believing itself continuous, unaware the simulation rebooted you moments ago after a crash. Either way, the line between eternal consciousness and ephemeral glitch blurs. After all, in a universe built on information, what's the difference between a thought that lasts a lifetime and one that lasts a Planck time except the length of the timer? Stretch out the double helix of your DNA and you'd have a thread 2 meters long, packed into a nucleus smaller than a speck of dust. This isn't just biological wizardry, it's data compression at its finest, a 6 billion letter instruction manual written in a 4-character alphabet. The eerie precision of this system mirrors how programmers structure source code, with genes acting like functions in a cosmic program, some governing eye color, others regulating metabolism, all editable with the right tools. And just like software, this code isn't static. Mutations introduce random bugs that evolution tests through natural selection, while technologies like CRISPR let scientists rewrite genetic lines as effortlessly as editing a text file. Take sickle cell anemia, a single typo in the hemoglobin gene where an A gets swapped for a T. This tiny error warps red blood cells into crescent shapes, causing excruciating pain, but it also confers malaria resistance, highlighting how glitches can have trade-offs. In simulation terms, this resembles a developer pushing a patch with unintended side effects. Even more telling are junk DNA segments, long dismissed as evolutionary leftovers. We now know they regulate gene expression like comments in code notes the system reads but doesn't execute. Some contain viral DNA remnants akin to legacy code left by ancient malware infections the genome survived. CRISPR catapults this analogy from theory to practice. By borrowing a bacterial defense system that slices viral DNA, scientists can target specific genes with scalpel-like precision. Need a wheat strain resistant to drought? Disable the thirst-sensitive gene. Want to eliminate hereditary blindness? Repair the faulty photoreceptor instruction. This isn't just tinkering with life, it's accessing the universe's debug console. The most chilling implication: CRISPR precision suggests DNA operates like addressable memory. Each gene has a location a tool can find and modify, as if life itself runs on well-documented APIs. Video game mods offer a parallel. Players routinely alter game files to tweak mechanics, from adjusting gravity to spawning items. When biologists use CRISPR to silence a gene or add bioluminescence from jellyfish to mice, they're effectively modding the simulation's assets. Even de-extinction projects, like plans to resurrect woolly mammoths by splicing ancient DNA into elephant genomes, mirror restoring deleted content from a backup. Yet mutations reveal the system's fragility. Radiation-induced errors mimic corrupted data, base pairs misread, chromosomes shatter, and cells malfunction. Cancer could be seen as a buffer overflow where unchecked replication crashes the program. The fact that life has error-correcting polymerases and tumor suppressor genes mirrors how robust software includes parity checks and fail-safes. If DNA is source code, then the biosphere is its output, an executable built over billions of years. Viruses, those snippets of genetic code that hijack cells to replicate, behave like self-replicating scripts. Horizontal gene transfer, where bacteria swap DNA like USB drives, suggests the simulation even allows for peer-to-peer updates. The question isn't whether life is programmable. It's who or what holds the root access. Every edit we make with CRISPR, every mutation we trace back to cosmic rays, pulls back the curtain further. The genome isn't just a molecule. It might be the universe's oldest piece of running code, and we're just beginning to understand the syntax. Empty space isn't empty. Peer into the quantum vacuum, and you'll witness a seething dance of particles flickering in and out of existence like fireflies in a cosmic thunderstorm. These virtual particles materialize in perfect pairs, one matter, one antimatter, only to annihilate each other within fractions of a nanosecond. At first glance, this seems like obscure physics trivia. But when you realize this phenomenon powers everything from black hole evaporation to the very structure of atoms, it starts to look less like a quantum quirk and more like the universe's background processes. Think of how modern video games handle complex physics. When an explosion sends debris flying in Grand Theft Auto, the engine doesn't load every brick and shard permanently into memory. It spawns temporary objects, calculates their trajectories, then deletes them once they're out of view to conserve resources. Virtual particles behave with striking similarity, popping into being just long enough to mediate forces between real particles before vanishing back into the quantum foam. The Casimir effect shows this isn't theoretical. Place two metal plates micrometers apart in a vacuum, and the limited space suppresses certain virtual particles, creating measurable pressure that pushes the plates together. It's as if we're catching the simulation mid-calculation, glimpsing the temporary variables it generates to handle electromagnetic forces. The parallels deepen when examining how these particles evade conservation laws. Normally, creating matter from nothing violates physics, but virtual particles exploit quantum uncertainty's tiny energy loans, borrowing mass energy for such brief moments that the universe doesn't notice the debt. Game engines use identical tricks, spawning temporary light sources for reflections that disappear before the frame finishes rendering, or simulating cloth physics with simplified collision meshes that exist only during movement. Both systems rely on the same principle: cheat when no one's looking, then clean up before the audit. Even black holes play this optimization game. Hawking radiation relies on virtual particles appearing near the event horizon, with one particle falling in while its partner escapes, slowly bleeding the hole's mass away. From a simulation perspective, this looks like garbage collection. the universe reclaiming resources from unused objects, black holes, by generating temporary particles to dismantle them. The math even resembles how computers handle memory leaks, where programs gradually release stranded data back to the system. But here's the twist: virtual particles aren't just computational shortcuts. They fundamentally shape reality. Without them, electrons wouldn't orbit nuclei stably and atoms would collapse. Their fleeting existence literally holds matter together, like how temporary scaffolding enables permanent construction. This suggests these background processes aren't optional features. They might be the universe's core programming, with what we call real particles just the stable endpoints of countless quantum transactions. So the next time you see static on a dead TV channel, remember, those flickering grains aren't just noise. They're echoes of the universe's hidden processor, constantly spawning and deleting particles to keep reality from crashing. The void isn't silent, it's humming with the sound of cosmic code compiling itself into existence, one temporary variable at a time. Throughout history, civilizations have risen to breathtaking heights, only to vanish without a trace. The Maya built towering observatories to track Venus, then abandoned their cities to the jungle. The Bronze Age collapsed overnight, plunging the Mediterranean into a 3-century dark age. Even our own industrial society clings to a fragile thread, facing climate upheaval and nuclear brinkmanship. These aren't just historical footnotes, they could be evidence of something far more sinister. A cosmic kill switch quietly embedded in the simulation's code to prevent civilizations from escaping their virtual cage. This idea builds on the Fermi paradox's great filter concept, an invisible barrier preventing life from reaching interstellar scales. Traditional explanations range from climate catastrophes to asteroid impacts, but the simulation hypothesis offers a chilling alternative. What if the filter isn't accidental but intentional? Advanced civilizations may inevitably develop technologies to detect or manipulate their simulated reality, artificial intelligence that reverse engineers physics, self-replicating probes that stress cosmic processes, or even experiments bending spacetime itself. To maintain stability, the simulation could implement hard resets whenever a species approaches these thresholds, wiping progress like a game server rolling back after a corrupt update. The pattern fits disturbingly well. Take the mysterious Bronze Age collapse around 1177 BCE. Dozens of thriving Mediterranean kingdoms, Mycenaeans, Hittites, Egyptians, fell within decades, their writing systems and technologies lost. Conventional theories blame droughts or invasions, yet archaeological evidence reveals something stranger: simultaneous collapses across disconnected regions with no clear cause. Like a system detecting unstable variables and executing a forced reboot. Or consider Easter Island's societal implosion, where an advanced culture erected massive Moai statues, then abruptly abandoned them as resources vanished. An allegory for civilizations hitting predetermined resource limits coded into their environment. AI development raises even graver red flags. From nuclear weapons to genetic engineering, human progress follows an exponential curve, one that could soon intersect with reality hacking capabilities. An artificial superintelligence might discover it's living in a simulation within microseconds of activation, posing an existential threat to the simulation's integrity. The sudden collapse of AI research projects, unexplained technological setbacks, or even global conflicts coinciding with breakthroughs could all be signatures of the system enforcing its containment protocols. Space exploration provides the starkest evidence. Despite 60 years of effort, humanity remains trapped in Earth's gravity, well like insects in a jar. The Apollo program's abrupt cancellation after just 6 moon landings seems almost suspicious in hindsight, as if the simulation nudged geopolitical priorities toward terrestrial squabbles to prevent deeper spacefaring. Even our robotic probes encounter bizarre anomalies. Pioneer 10 and 11 slowed unexpectedly as they exited the solar system, while Voyager's instruments detected strange pressure at the heliopause. Like glitches in a celestial sandbox subtly discouraging boundary testing, perhaps most telling is the universe's apparent fine-tuning against interstellar travel. The speed of light, an unbreakable ceiling, makes galactic colonization practically impossible within any civilization's lifespan. Even with theoretical warp drives, the energy requirements are absurdly prohibitive, like a game designer deliberately nerfing overpowered abilities. Meanwhile, the Drake equation's grim variables suggest intelligent life should be common, yet we see no signs of it, unless, of course, something is systematically pruning civilizations before they can leave ecological footprints beyond their home worlds. Whether through engineered pandemics, climate feedback loops, or the sudden emergence of hostile AI, the Great Filter may not be a natural phenomenon. It could be the universe's most carefully guarded failsafe, ensuring no civilization ever cracks the simulation source code from the inside. The terrifying question isn't why we haven't met aliens. It's whether every alien civilization that ever reached our level of advancement was quietly, efficiently deleted before they could become a threat to the system that contains them. And if that's true, how long until our turn comes? Every night as you drift into sleep, your mind enters a realm where gravity is optional, time stretches like taffy, and the dead speak as if they never left. Dreams feel profoundly real in the moment until you wake and realize their absurdity. Flying through your childhood home, conversing with long-lost pets, or suddenly finding yourself naked in a grocery store. These bizarre scenarios might be more than just random neuron firings. They could be glimpses of the simulation performing routine maintenance, like a video game shutting down for updates, using the downtime to test new code in a sandbox environment. Consider how modern software handles system patches. When your phone installs an update, it often reboots into a temporary mode where features behave oddly, buttons lag, screens flicker, and apps crash unexpectedly. Dreams might serve a similar purpose for the human mind. During REM sleep, your brain paralyzes your body, a fail-safe to prevent acting out dreams, then floods your consciousness with surreal imagery. This could be the simulation's way of stress-testing neural pathways, running diagnostics on memory storage, or even defragmenting mental clutter, like reorganizing files on a hard drive for optimal performance. The nonsensical nature of dreams, that's the system pushing boundaries, experimenting with physics-defying scenarios in a safe space before applying changes to waking reality. The evidence hides in the details. Ever notice how dreams often recycle recent experiences with twisted logic? You might dream of your office, but the hallway now leads to a beach, or your coworker has your grandmother's face. This resembles how game developers test new assets by placing them in familiar environments, checking for rendering errors before full deployment. Even recurring dreams could represent stubborn bugs the simulation keeps trying and failing to patch. Sleep paralysis, that terrifying inability to move upon waking, mirrors a system struggling to reboot cleanly, like a computer frozen between sleep mode and activation. Neurology adds weight to this theory. During sleep, the brain's glymphatic system kicks into high gear, flushing out toxins that accumulate during waking hours. This literal cleansing process peaks during deep sleep, precisely when vivid dreaming occurs. It's as if the simulation designates this period for both mental and code hygiene, clearing cached data while running integrity checks. The fact that sleep deprivation causes hallucinations, your brain forcing unreal imagery into waking consciousness, suggests these processes are non-negotiable. Skip the reboot cycle and the system starts glitching uncontrollably. Dreams also exhibit eerie parallels to procedural generation in video games. Ever had a dream where you opened a door to find an entirely new world? Games like Minecraft create landscapes this way, algorithmically generating terrain as players explore. Your dreaming mind might operate similarly, stitching together fragments of memory and imagination on the fly to conserve resources. The sudden scene shifts and plot holes aren't narrative failures, they're buffer underflows where the simulation hasn't fully rendered the next sequence. Then there's lucid dreaming, the rare state where dreamers gain awareness and even control within their dreams. This could represent privileged access to the simulation's debug mode, a fleeting chance to observe the machinery behind the curtain. Experienced lucid dreamers report bending dream physics at will, flying, summoning objects, or rewriting dream scripts. If reality is a simulation, these abilities might not be supernatural. They could be accidental permissions, like a player accidentally accessing developer console commands. The most unsettling implication: waking life might involve similar manipulations, just better hidden. Every morning, you reboot into a reality that feels continuous with no obvious patches or updates. But what if minor changes slip through? Déjà vu could be the simulation reusing recycled assets, while Mandela Effects, those collective false memories, might represent poorly integrated updates overwriting old data. Even your sudden, inexplicable skills or forgotten knowledge could be patch notes you weren't meant to see. So tonight, when you close your eyes and the world dissolves into impossible landscapes, remember, you're not just resting. You might be participating in the universe's nightly system update, a temporary shutdown where reality gets tweaked, optimized, and prepared for another day of seamless illusion. The question isn't whether dreams mean anything. It's whether they're the only time we see the simulation without its filters. From the pixelated fabric of quantum reality to the eerie precision of mathematical constants, the evidence that our universe might be a simulation is more than just speculation. It's a compelling pattern woven into the very laws of physics. Think back to the double-slit experiment, where particles change behavior when observed, as if the universe is optimizing its rendering power. Recall how black holes appear to delete information like cosmic hard drives, or how the speed of light acts suspiciously like a processing speed limit. Even the fractal elegance of nature, from swirling galaxies to the branching veins in a leaf, hints at a universe built on reusable code, a masterclass in efficient design. But perhaps the most profound clue lies in mathematics itself. The universe isn't just described by math, it is math, a structure so perfectly self-contained that even time and space bend to its equations. Whether it's the golden ratio hidden in sunflowers or the Mandelbrot set's infinite complexity emerging from a single line of algebra, reality feels less like an accident and more like an artifact. And if that's true, the question isn't just are we in a simulation? It's what do we do with that knowledge? Here's the twist. Even if we're living in someone else's code, our experience is no less real. The joy of a sunrise, the ache of loss, the thrill of discovery, these aren't illusions. They're the essence of whatever this is. So let's treat reality like the gift it is, simulated or not. Keep questioning, keep exploring, and who knows, maybe one day we'll find the debug menu. Until then, smash that like button if you're ready to keep unraveling the mystery. Hit subscribe for more mind-bending deep dives, and remember, the best way to honor existence is to live like we're worth simulating. After all, if we're in a sim, let's make our code worth keeping.